Hello everyone, I'm pleased here to introduce our work ELD, Adaptive Detection of Malicious Nodes under Mix-Energy-Depleting Attacks using Edge Learning in IoT Networks. In this presentation, I want to introduce our work by the following four parts. The first one is background and motivations. The second one is the detail of edge learning detection. And the third one is the evaluation of it. Finally, we make the conclusion about future work. In this work, we consider the situation that IoT networks suffer from the insider energy depleting attack. And we consider three different attack cases. The first one is flooding malicious traffic. And in this case, for example, when the attacker hacks a device, he will use the device to send flooding packets to another device to consume its energy. For example, the D1 sends flooding packets to D2 so that the energy of D2 is wasted. And the second one is the carousel malicious traffic. For example, when N1 needs to send packets to the base station, it will request the N3 to send the packets to N4. But the N3 will transfer the packets to the N2 maliciously. According to the normal rules, the N2 will send the packets to N1 back, so that in this circle, the packet is transferred in this circle again and again, and the energy of N1 and N2 will be wasted. And the third case is the replay malicious traffic. For example, when the N6 transfer the package to the N5, and the N5 copied the package to be multiple redundant packets, and request N4 to transfer this package to the base station. So the energy of N4 will be wasted. To solve these attacks and identify malicious nodes, we have the following challenges. Existing work focuses on a single attack scenario. So in this work, can we focus on multiple mixed attack scenario? That means a lot of different attacks happen at the same time. Existing works only detect anomaly, but in this work, we hope we can locate malicious end devices. In the IoT networks, most of devices are resource constrained. So can we achieve detection with a lightweight weight? And a lot of mechanisms focus on narrow applied detection. But we want to propose a general framework without changing the protocol of network. And a lot of mechanisms relies on label data in advance. But we want to learn from practical environment and keep improving our performance of model according to the detection results. So to solve these challenges, we propose our ELD. The workflow of ELD has two main parts. The first part is intrusion detection, which is used to identify malicious traffic. And the second one is malicious nodes detection, which is used to identify malicious nodes. In the intrusion detections, it starts from the traffic logs, which is generated by end devices, and is used to record the history of the communication between end devices. And the base station will collect these logs regularly, for example, every 30 minutes. And the base station can construct edges based on these logs. Edge is the structure to record the direction of main traffic. Edge, which we will introduce later, edge can be input to the random forest model to be classified. Just like we mentioned before, we hope ELD can reduce the relying on the prepared data set so that we hope it can label edge automatically to provide the data to train its model itself. And we call this mechanism the damage node identification. After the edge classification, intrusion edges can be used to build an intrusion graph. According to the graph, malicious nodes can be identified and located. Now we introduce the traffic log model. The traffic log models includes the senders of the packet and the receiver of the packet, and the time when the packet is received by the node, and the size of the packet, and the protocol type used for transferring the packet. We use some features to identify whether an edge is malicious. For example, like the duration average and the standard deviation of the number of packets and the average of the size of packets, which can be extracted from traffic logs. And these data are built based on the UNSW MB15 dataset. Now we give an example about the edge generation. For example, these are the traffic logs of M1. That M1 receive packet 1 from M2 and receive packet 2 from M3 and receive packet 3 from M2 and receive packet 4 from M4 and so on. So we can find that the main traffic is from M2 and we ignore the traffic from M3 and M4 because this can help us to reduce the complexity of the graph. So that according to these logs, we can build an edge like this. These features are based on the features we mentioned before. And we label this to be the edge 1, and it can be input to the random forest model to be classified to be intrusive edge or an not intrusive edge. To label traffic automatically, ELD thinks the traffic received by damaged node is malicious traffic. But many IoT nodes may have different battery capacity and various energy overhead. So there is no unique metric to determine whether a node is damaged. Therefore, we detect damaged nodes according to their abnormal speed of receiving packets. That we set a thread for each node to determine whether their receiving speed is abnormal. And it's denoted by the RI. And we define the RI like this. The RI, considering different devices located on different places of the network. For example, like this road, the M6 locates on the main road of this road, so that the speed of each receiving packet should be higher than other nodes. And the M1 is the first node of this road, so the receiving speed of it should be 0. Then we define the RI like this equation. We think the RI should be the sum of the pre-nodes of RI plus the speed of the pre-nodes of RI sending packets. And now, according to this formulation, we assign different RI to each node to determine whether they are damaged. To further improve the performance, ELD adjusts its setting by adaptability optimization. There are 2 periods of ELD. The first one is adaptation period. In this period, all edges constructed from traffic logs can be labeled as not intrusive. And from this period, ELD can obtain a base model. And the second one is the detection period of ELD. The detection of ELD will be executed for multiple rounds. In the first round, that's when damaged nodes are detected. If the pointy of an edge is damaged, then ELD will label this edge to be intrusive. And from the second round of the detection period, there will be 4 cases. Case 1 is the node is identified as damaged and is pointed by an intrusion edge. Case B is the node is identified as not damaged and is pointed by an intrusion edge. We call this potential damage. And in this case, we should reduce the RI. And in the case C, the node is identified as damaged and is not pointed by an intrusion edge. And in this case, there are 2 possibilities. The first one is RI is set to low so that it causes some false alarm. Or the case 2, there are novel attacks that are not learned by the model, so that the ELD should label this traffic to be malicious. And in the case D, the node is identified as not damaged and is not pointed by an intrusion edge. But consider the case C. We don't know whether which cases is correct for the determinant of ELD, so that we consider both cases, just like this graph. In the adaptability optimization, in the adaptation period, ELD can obtain a base model, but after the detection 1, the base model will learn something and become model 1. To the detection round 2, if the model 2 faces the condition that is mentioned in the case C, it will create 2 branches, which means each branch will consider the specific condition, just like we mentioned like this. One branch is consider case 1 and one branch is consider case 2. So that just like this. The model 2 will create 2 branches to become model 2A and model 2B, just like this. Now, after the adaptability optimization, which identify the malicious nodes, is the task of intrusion graph. And this is the example to illustrate the intrusion graph generation. For example, we have this edge 11, edge 21, edge 12, and so on. And we join different edges to be different graphs. And we for example, we put the edge 11 and edge 21 to be graph 1 because their timestamps are close to each other. Assume we have the detection result just like this, and then we can use it to build an intrusive graph, and just like this. So now we can know the M1 and M4 are malicious nodes. About the malicious node identification, we have 2 principles. The first one is the first node of an intrusion path can be identified as malicious. And the second principle is for each node of a loop, if there is another intrusion edge pointing to this node and the pointer of the edge is not in the loop, then the node should be identified as benign. Otherwise, it should be malicious. For example, like this graph, there is a loop, but N2 is pointed by N1, which is out of the loop. So that N1 should be malicious, N4 should be malicious, but N2 and N3 should be benign. And the ELD will execute multi-rounds, so it may cause multiple branches with continuous detection. For example, by 4 rounds of detection, in the final round there could be 8 branches, and it's the maximum cases. Only those malicious nodes appeared over half of branches. For example, 4 branches can be determined as final malicious nodes. Now we introduce the evaluation of ELD. And in this simulation, we deploy the IoT network to 100 multiply 100 square meters rectangle area. And each node's communication range is 10 meter to 50 meter. Each experiment is executed in 10 runs with 10 different networks. And the number of loops caused by carousel attacks can vary from 20 to 50. For flooding attacks, malicious nodes can send 15 to 18 packets one time to another node or base station in every 15 minutes with attack probability. For replay attacks, the number of replay packets can vary from 10 to 20 when a replay attack happens with attack probability. In the network, nodes can generate traffic logs and send these logs to base station in every 13 minutes. Now we introduce the impact of the number of nodes. With the number of nodes as 7, 12, 17, 22, and 27, we can find that it's easy to detect malicious nodes in a small-scale network for 3 different mechanisms. But it's hard for HD to detect malicious nodes in large-scale network. And with the probability of multiple mixed attacks to be 0.1, 0.3, 0.5, and so on, we find that high attack probability is beneficial for ELD. And it's hard for HD and PDE to handle over high attack probability. With the number of passing packets to be 100, 500, and so on, we find more packets improve the accuracy of HD and PDE. ELD outperforms other schemes. With the attack types to be carousel attack, flooding attack, replay attack, and Mix-Energy-Depleting-Attack, we can find PDE outperforms ELD, especially in the carousel attack, because it has a unique mechanism to record the history of the path that packets passed on, so that it has a very outstanding performance. But in the flooding attack, only ELD can detect, because HD and PDE focus on detect those abnormal packets. But in this attack, all packets can be legal, so only ELD can detect them. And in the mixed energy depleting attack, ELD outperform other 2 mechanisms. Finally, we make the conclusion and give our future work. ELD can provide a better detection rate by around 5% to 40% as compared with 2 detection schemes. And in this work, we assume that all traffic logs collected by the base station are credible. But in practical environment, malicious node may modify the traffic logs. So we decided to solve this by comparing the sending packets logs from senders with the receiving packets logs from receiver, so that we can know some conflict happens in the traffic logs. And we just ignore those traffic logs with conflict. And we also consider how to detect carousel malicious nodes by using more information, because the performance of ELD in detecting this kind of attacks is not so good. And we decided to solve it by recording all the passes that a packet may pass. And this is the mechanism called provenance. And that's all. Thank you.